Welcome to the class. This is the first class. What we are going to see in this class is all about the basic thermodynamics. Basically, it is all about a review of the thermodynamics. Let's see first the terminologies which are very basic in the course of thermodynamics. First is we have to define what do we mean by thermodynamic system. Thermodynamic system is defined as quantity of matter or a region in the space chosen for the study. So, we basically are interested in specific region, or we are interested in specific mass, amount of mass about which we are going to have interest, for which we are going to study. So, that mass or that region is called as thermodynamic system. So, then we have few types of systems. What we are going to define them based upon the boundary of the system. So, system with fixed boundary. So, let us consider a point that we have a pot in which we have water and we have kept a lid on the pot. So, this is a system which has air plus water, and then this is fixed with the boundary. So, this is called as the system with fixed boundary. Then we will have system with moving boundary. So, in case of system with moving boundary, we can consider a piston cylinder arrangement where we have a cylinder and that cylinder is fitted with a piston inside, and if we can supply heat or we can take away heat from the gas which is placed inside, then accordingly piston can move up or down. In such case, the boundary of the system is moving. So, this is also a system where we are focused on certain mass inside the piston and cylinder arrangement, where one of the boundaries is moving. So, this is the example of system with moving boundary. We might encounter a situation where we will have a system and then we have to define boundaries for the system. As an example, we can take an example of candle, where we have flame of the candle and then we define this region as our system. If we define this region as our system, then we are defining this as our region of interest for thermodynamic studies. Hence, such system which does not have fixed boundaries and where a user defines the boundaries, but there we can see it as these are the imaginary boundaries and they are not physical boundaries of the system. Then, by defining the boundaries of the system, we are defining certain region, or by focusing upon certain mass, we are focusing certain mass of the system. However, then it comes that we are excluding certain mass and we are excluding certain volume. So, the volume or mass which is not considered or which remains outside the system is called as surrounding. So, everything outside to the system is called as surrounding. So, now these two are the basic things related to thermodynamics. Having said this, now we will see what are the different types of the system. So, first type of the system is closed system. Now, let us see the types of thermodynamic systems. So, first is closed system. In case of a closed system, suppose this is our system of our interest, and then this is surrounding. In case of closed system, we can have certain heat going out of the system, certain heat coming into the system. We might have W out of the system, we might have W into the system, but we will not have mass entering into the system. The system which can have interaction with the surrounding in the form of heat and work only is a definition of closed system. Then we will have open system. So in case of open system, again we will consider an open system, and in case of open system we will have certain work which is delivered by the system. There might be certain work input to the system, there might be also heat input to the system, and there might be heat output from the system, or system might reject certain amount of heat. But apart from that, there might be certain mass m dot entering into the system, there might be certain m dot or mass leaving out of the system. So in such case, where system can have interaction with the surrounding from the perspective of mass, heat and work is called as open system. And we have many such examples in engineering which are open systems, which have something like heat exchangers, we have compressors, pumps, turbines. These are the examples of open system. In case of closed system, we have piston and cylinder arrangement which is not having any walls, or rather if at all there are walls, and walls are closed, and such system would be the example of closed system. Then we have an isolated system. So in the isolated system we have only system and surrounding, and there is no work interaction, there is no heat interaction, and then there is no mass interaction between the system and the surrounding. In such case, the system is called as isolated system, and the best example for isolated system is the thermos flask. So these are basically types of thermodynamic systems. Then we have next part to study is properties of system. So we will define properties of system. We have to define what do we mean by property of a system. So property of a system is characteristics of the system. Basically, why do we need to do this? Suppose we are interested to study thermodynamic behavior of a system, then we have to describe the existing state of the system, and then we might need to understand the change in state of the system. So for that we have to describe the existing position or existing state of the system. So this characteristics of the system helps us to define the existing state of the system. So the properties are the characteristics which help us to define the state of the system. But then within the properties there are again two types, and there is an extensive property which depends upon mass and extent of the system. So the extensive property example is total mass, total momentum and total volume. So we have some properties which are helping us to describe the state of the system, but they need the extent of the system, or they also need what is the size of the system. But then there are certain properties which are independent of the mass and size of the system or extent of the system. Such properties are called as intensive properties of the system. And we know the famous example is pressure, also we have temperature and density. Further, any specific property of the system is intensive in nature, something like specific enthalpy, specific entropy, specific internal energy, and all these properties would become intensive properties of the system. Then, as what we said, that we need the properties of the system to describe a particular state of the system, and that particular state of the system is called as thermodynamic state. So a set of properties which help us to describe the condition of the system is called as thermodynamic state. So we will suppose we are dealing with a piston and cylinder arrangement, and then in the piston and cylinder arrangement we have gas which is suppose at 12 bar pressure and 500 degrees Celsius. Then these two things, which is 12 bar and 500 degrees Celsius, are basically the properties of the system, which is gas, which we are using to describe the state. Upon certain interaction with the surrounding, this suppose next state of that gas is 10 bar and 400 degrees Celsius, then the 10 bar and 400 degrees Celsius is next state of the same system. So these are the ways by which we define or describe the condition of the system. Then we basically have to define equilibrium. Here we are basically in thermodynamics mainly dealing with the equilibrium of the system. So thermodynamics largely deals with equilibrium of the system, and equilibrium is necessarily balance of properties which are used to define the condition or state of the system. Hence, equilibrium state of the system, when it is achieved, then we will not have any unbalanced force within the system which will change the properties of the system. So once we have defined an equilibrium, or once an equilibrium is achieved by the system, then there is no change in the properties or any property of the system, since there is no driving force. What are the basic driving forces which we would know? If there is non-uniformity in pressure within the system, then there will be flow from high pressure to low pressure region. If there is density change or density variation within the system, then there is flow from high density part to the low density part. If there is variation between in the temperature of the system, then there is flow of heat from high temperature to low temperature. So this flow of mass or heat is mainly occurring due to the presence of the some driving force, and that driving force is absent when we say that system has reached an equilibrium. So once we have got system in equilibrium, its all properties are fixed. Then there are internally many equilibriums which are defined, and then first equilibrium is mechanical equilibrium. Here system is said to be in mechanical equilibrium once the mechanical forces are balanced within the system. So there is no unbalanced force, mechanical force for the system, or for us we have pressure is uniform within the system. Then we have thermal equilibrium, and in case of thermal equilibrium there is no temperature variation within the system. Then chemical equilibrium, then there is uniform composition of the system. So once we have pressure uniformity, once we have temperature uniformity, and once we have basically composition uniformity, then system is said to be achieved the thermodynamic equilibrium. So system needs to be brought to thermodynamic equilibrium for the understanding, and thermodynamic equilibrium will be achieved when we have mechanical equilibrium, thermal equilibrium, and chemical equilibrium. Then next part to discuss is thermodynamic process. So any change that system undergoes when one equilibrium state to other equilibrium state, system undergoes. So when system undergoes from one state to other state, in the previous example we had said that there is a gas in a cylinder which has certain pressure and temperature at an instance, and after certain instance there is certain other pressure and certain other temperature. So the first state of the system and the second state of the system, they are basically different. So in such case system has undergone a process, and this is what we are calling it as a thermodynamic process, where system undergoes from one state of equilibrium to other state of equilibrium, and the final destination which system has basically achieved, before that equilibrium to achieve, system has undergone through various destinations or various milestones, and those all milestones are basically the intermediate thermodynamic states which system would have in equilibrium, and all such states if we join, then we say that this is the path which system has followed to execute a particular process. So, these are the two things which are related with change in state of the system. Then we have types of processes. The first type is something like, suppose we are considering processes in a closed system. So, when we are considering process in a closed system, then basically we are looking into two different time instances, as what again we will refer back to our previous example, where we have said that there is a piston cylinder arrangement in which there is gas, and that gas has certain pressure and certain temperature, and then there was certain interaction of work and heat between the system and surrounding, and then the gas has attained certain else pressure and certain else temperature. So, this certain else pressure and temperature is at certain else instance for the same mass, and then that certain else pressure and temperature is what the next state of the systems. So, initial and final, they are the same, they are the states of the same system, but they are at two different instances. When we are looking for the processes in open system, we have to consider an example here, that there is certain inlet and certain outlet for one system. This is system of our interest, and for this system, this is in and this is out, and this is station 1 and this is station 2. The system has certain mass entering in at station 1. So, that mass has certain property, and there is certain mass which is leaving at station 2, and that has certain property. So, while analyzing this open system, we consider that the properties at station 1, and we will consider properties at station 2. Then this is what the change in the conditions which mass has undergone, and these will be used for analyzing the open system. So, here practically, while considering processes in the open system, we are looking at two different stations at this, maybe at the same instance. So, we are looking at the same instance, but at two different locations, while understanding the process which is undergone by the open system. Then there are other types of processes. First is a reversible process and an irreversible process. System is said to be undergone an irreversible process when system cannot come back to its original state by the same path. So, if we try to draw a PV or TS diagram, suppose we are trying to draw a TS diagram and system is going from one state to other state, and then in such case we don't know what is the path followed by the system, then in such case system will undergo an irreversible process, since it cannot come back to the same state by the same path. But if we know, then the system has undergone certain process and then system can come back to the same state, then we can draw a firm line between the two states where system is said to be in equilibrium at all points, and such process where system is guaranteedly coming back to original state by the same path is called as a reversible process. Then we have cyclic or non-cyclic process. In case of cyclic process, suppose we will take a PV diagram and then system is at state 1, which is having certain pressure and certain temperature. System has undergone multiple changes and system has come back to the original or initial pressure and temperature. Then, since system has come back to the original state, it is called as a cyclic process. If system doesn't come back to the original state, which was 1, and goes back to state 2, it does not come back to state 1. Okay, so this is a non-cyclic process. Then we have adiabatic process or isentropic process. Adiabatic process is a process in which there is no heat interaction of the system or with the system and between system and the surrounding. So, but if the process is executed reversibly, then reversible adiabatic is also termed as isentropic process. So, if we try to plot TS diagram for an isentropic process, then TS diagram becomes vertical. So, if we are at state 1, then we will go to state 2 with constant entropy. So, it becomes a straight vertical line. But if we try to draw a PV diagram for isentropic curve, then we will have a curve of this kind in case of state 1 to state 2. So, this becomes isentropic compression, and if we want to do expansion, then 2 to 1 becomes the expansion process, which is isentropic. Having said this, we have next, which is an isobaric process. So, isobaric process, as the name suggests, it is the process where pressure is kept constant. So, if we try to plot PV diagram, then the process 1 to 2 is the isobaric process where pressure is constant. Otherwise, if we try to plot TS diagram for the same isobaric process, suppose we are considering heat addition between 1 to 2, then the process is like this, and if we are considering heat rejection, then the process is 2 to 1. Then we have isothermal process. As the name suggests, isothermal process is a process in which temperature of the system is going to remain constant. So, if we plot TS diagram, then the process 1 to 2 is having constant temperature. So, it is an horizontal line. So, that horizontal line represents the isothermal process. But if we try to plot PV diagram for the isothermal process, then it would look like similar to the isentropic curve, and then that curve will have negative slope as 1 to 2, which is compression process, or 2 to 1, which will be expansion process. Then we have isochoric process. As again the name suggests, we will have isochoric means volume constant process. So, it becomes 1 to 2 process, which is a complete vertical line on PV diagram. So, the TS diagram for constant volume process would be similar to that of constant pressure process, but it will be more steeper. So, this is 1 to 2 process for heat addition, or there can be 2 to 1 process for heat rejection in constant volume sense. So, as the name suggests, we have different processes which system would undergo. Now, let us see some laws of thermodynamics. So, we have first zeroth law of thermodynamics, And zeroth law of thermodynamics states that if system A is in thermal equilibrium with system B and system B is separately in thermal equilibrium with system C, then system A and system C are said to be in thermal equilibrium. Basically, zeroth law of thermodynamics has one clear hint that temperature is property of the system, and then this is the definition for the temperature, or this is the definition for thermal equilibrium. Then we have first law of thermodynamics, which is basically energy conservation principle. It states that energy can neither be created nor be destroyed in a process, but one form of the energy gets converted into other. Then this law of energy conservation has many implications in understanding the system, and it helps us by having its mathematical formulation available and in the format of energy conservation equation. Basically, thermodynamics in general deals with different forms of energies and their interaction with the system and the surrounding. We have basically different forms of energies. The forms of energies, something like work and heat. Work and heat are two different forms of energies. So then we will have some mechanical work, we will have electrical work, we have shaft work. So these are different kind of works which are there, and then we have heat as again a form of energy. We have kinetic energy, we have potential energy, and then we have internal energy. So there are different forms of energies which are involved in the thermodynamics of a system whenever we are dealing with understanding of a system. Then first law of thermodynamics, when we apply for the cyclic process, it states that cyclic integral of heat is equal to cyclic integral of W. So this is the mathematical statement of first law of thermodynamics for the cyclic process which is undergone by the system. Maybe it is closed or maybe it is open. Then we have equation for non-cyclic process, and suppose in the closed system, then the differential form states that dq is equal to dE plus dW. It states that if Q amount of heat is supplied from the surrounding to the system, then system does dW amount of work, and rest of the energy change of the system is dE, where E is total energy of the system, which will have three energies, basically D of internal energy, there is kinetic energy, and then there is potential energy. So when we are not considering any kinetic and potential energy, then first law of thermodynamics for closed system will be du plus dW is equal to dq, or dq is equal to du plus dW. So this is expression for first law of thermodynamics applied to non-cyclic process in a closed system. And then we have non-cyclic process in a open system. Again, understand the similar example where we have certain mass which is entering into the system and certain mass amount which is leaving out of the system from station 2, and in station 1 we have entry of mass into the system. Then we can write down the equation as, suppose then there is certain work done by the system, there is some heat addition to the system, then if we consider all, then equation becomes m dot, which is mass flow rate, which is for the entering into the system, and that is multiplied by H1 plus V1 square by 2, which is the kinetic energy, plus GZ1, which is potential energy, plus Q dot is equal to m dot 2 into H2 plus V2 square by 2 plus GZ2 plus W dot. So this is the steady flow energy equation, and since we are telling that this is a steady flow energy equation, m dot 1 has to be equal to m dot 2 since there is a steady state. So the same amount of mass flow rate is taking place at the inlet and also at the outlet. So this is the equation for non-cyclic process for an open system. Then we have second law of thermodynamics. Basically it has two statements, and the first statement is Kelvin-Planck statement, which states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So practically, if we have a thermal energy reservoir and then that thermal energy reservoir is interacting with a system which is undergoing a cyclic change, and then we say that it is giving Q amount of heat and system is doing W amount of work, where no heat is rejected. So if no heat is rejected, then Kelvin-Planck statement says that it is impossible to construct such a device which operates in a cycle and interacts with only one reservoir. But then there is a second statement, which is Clausius-Planck statement, which states that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from low temperature body to high temperature body. So practically it says that there is a warm space and there is a cold space, and among these two spaces there is a system which is undergoing certain changes for that, and with as an effect of those of cyclic changes, it is taking QL amount of heat from the cold space and putting QH amount of heat in the warm space, but it doesn't interact with surrounding or anything and gets any work input. So this is impossible from the perspective of Clausius statement. Having said this, we have Clausius inequality, and Clausius inequality states that cyclic integral of dq by t is always less than or equal to 0, and this is for a cyclic process. But if there is a reversible process, then it states that dq by t for a reversible process is equal to ds. So where second law of thermodynamics states that entropy is a property of system. As what we have seen, 0th law has a correspondence with temperature as property of a system. First law has correspondence with internal energy or enthalpy of the system as the property of the systems, and then second law of thermodynamics tells that entropy is the property of the system. So for reversible process, change in entropy is equal to dq by t. But if it is an irreversible process, then ds is not equal to dq by t, but ds is greater than dq by t. But then we have to integrate it from state 1 to state 2 for the system, and otherwise ds is greater than or equal to dq by t. And if we are interested to find out total change in entropy of the system, then we have to integrate and find out what is the ds. But for the irreversible process in a system, we have ds greater than or equal to dq by t. So, integration 1 to 2 ds is greater than or equal to dq by t. But for such irreversible process, we can still say that 1 to 2 is equal to 1 to 2 dq by t, but we have to add one thing which is called as Sgen or entropy generated. So, this is Clausius inequality. This Clausius inequality helps us to decompose any reversible process into the multiple isotherms and adiabats. So, consider that we have a PV diagram where system has undergone a process 1 to 2, then this process 1 to 2 is any arbitrary reversible process, and this arbitrary reversible process can be decomposed into multiple things, multiple processes. So, this is 1 to 2, 1 to A to B and B to 2. 1 to A is an adiabatic process, 1 to 2 is an adiabatic process. So, A to B is an isothermal process and B to 2 is again an adiabatic process. So, the process which is a general reversible process got decomposed into 3 processes which have 2 adiabats and 1 isotherm. So, this is what we are telling, that we have help from Clausius inequality, that it helps us to decompose the reversible process into multiple things. Basically, we try to say here that the work and heat interaction in the actual process 1 to 2 is same if we don't consider 1 to 2 and if we consider the other 3 set of processes which system actually undergoes between points 1 to 2 or in states 1 to 2. Other thing which we get help is we can decompose the cycle into multiple isotherms and adiabats, as this is a non-cyclic process. Similarly, if we have a cyclic process, then the cyclic process can again be decomposed into multiple processes which are isotherms and adiabats. So, this is an adiabatic process and then this is an isothermal process. So, we can now say that the area under the isotherms and adiabatic processes is same as the area under the closed cyclic process. So, we can state that this part can be dealt with these isotherm, this adiabat and then this isotherm and this isotherm. So, this becomes, if I number A, B, C and D. So, we got A, B, C, D as one patch, then we will have other patch here and then we will have other patch here. So, like that we can decompose the complete cycle into multiple isotherms and multiple adiabats. And we have an advantage of such decomposition of cycle, which is a closed cycle, which is basically due to the fact that system has undergone a process and came back to its original state, and such cyclic process gets decomposed into multiple adiabats and multiple isotherms. So, now let us see the thermodynamic cycles, which are basically the cyclic processes composed of different processes individually with different characteristics. So, first cyclic process which we would consider is Carnot cycle. Actually, importance of these cyclic processes is that some of these cyclic processes have engines based on their thermodynamic characteristics. So, first cyclic process which we would consider is a Carnot cycle. So, let us draw the PV diagram and TS diagram for the Carnot cycle. So, here we will have first PV diagram, pressure on y axis, volume on x axis, and as per the PV diagram of this cycle, we have process 1 to 2 as the isentropic compression, process 2 to 3 as isothermal heat addition, process 3 to 4 as isentropic expansion, and process 4 to 1 as isothermal heat rejection. So, these are the processes which are basically comprising of which is constituted towards the formation of Carnot cycle. So, let us draw the TS diagram for Carnot cycle, and here we have temperature on y axis and entropy on x axis. Process 1 to 2 is practically entropy constant cycle process. So, this process 1 to 2 is isentropic process, so it is a vertical line 1 to 2. Process 2 to 3 is isothermal process, so it is a temperature constant line, so it will be a horizontal line in 2 to 3 process. And then 3 to 4 is again entropy constant line, which will again be a vertical line in the TS chart, and process 4 to 1 is again temperature constant line, which would be a horizontal line in case of TS diagram. So, this is a Carnot cycle. Now, this cycle is an ideal cycle where all processes are reversible. Now, let us move towards the next cycle, which is Otto cycle. We are interested to see this specific part in the overview of thermodynamics because these cycles constitute the engines which are the complementary engines towards our gas turbine. So, Otto cycle is basically leading to SI engine, which is a spark ignition engine. So, PV diagram, or in our case we call it as petrol engine. So, PV diagram for Otto cycle is comprised of first 1 to 2 is isentropic compression, 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is again constant volume heat rejection. So, this is entropy constant, this is volume constant, this is entropy constant 3 to 4, and 4 to 1 is again volume constant. So, this diagram on TS chart would look like this, where process 1 to 2 is isentropic, so it will be a vertical line, 2 to 3 is constant volume heat addition, so this is constant volume heat addition, 2 to 3, 3 to 4 is isentropic process expansion, so this is 3 to 4, and 4 to 1 is again constant volume heat rejection. So, Otto cycle basically is having constant volume heat addition and constant volume heat rejection. So, based upon this there is design of SI engine or petrol engine. Then next is the diesel cycle. So, for diesel cycle we also know that there is diesel engine and it is also an internal combustion engine, and PV diagram for this diesel engine is like this, where we have first 1 to 2 process is same as isentropic compression, then at 2 we have constant pressure heat addition from 2 to 3, 3 to 4 is isentropic expansion, and 4 to 1 is constant volume heat rejection. So this is entropy constant, this is pressure constant heat addition, this is entropy constant expansion, and this is volume constant heat rejection. So this is the diesel cycle. So the diesel cycle on TS chart would look like this, where 1 to 2 is isentropic process, 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion. So it is a vertical line, and then we have 4 to 1 as constant volume heat rejection. So these are the 4 processes which constitute the diesel cycle. So we know that we use diesel as the fuel for the diesel cycle and petrol as the fuel for Otto cycle, but there are many other variants which can be used. So petrol SI engine basically can have other fuels like CNG or LPG or biogas, and then there are new kinds of biodiesels which can also be thought in the blending or in isolated usage for the diesel cycle. Then we have Rankine cycle, and this Rankine cycle, we know here working medium is water, and this water is used in two phase. So this cycle uses two phase material while doing the work. So the PV diagram for this cycle basically needs first to draw the phase change dome. Then 1 to 2 is isentropic, 1 to 2 is basically isentropic compression, but since we are dealing with liquid, so we will not see much compression, but there will be much pressure rise. Then 2 to 3 is constant volume heat, is constant pressure heat addition. Then 3 to 4 is isentropic expansion, and 4 to 1 is the constant pressure heat rejection. And TS diagram for this would be again needing the dome, where 1 to 2 is basically isentropic compression, 2 to 3 is constant pressure heat addition, and 4 to 1 is constant pressure heat rejection. So this cycle is giving us a thermal power plant, which is a steam power plant, and steam power plant has water as working medium, which is in liquid state in the 1 to 2 process, which will get converted into vapor state in the process 2 to 3. So 3 to 4 we will again have water in the vapor state, but 4 to 1 again there is a phase change. So this is a basic cycle which is again used for electricity generation, or in olden days it was used for locomotives, where one engine, which is steam engine, which was based upon this cycle. Now the last cycle which is of our interest is Brayton cycle, and Brayton cycle is the cycle upon which we have our gas turbine power plant based upon. So PV diagram for gas turbine power cycle is like this. So we have 1 to 2 isentropic compression, then 2 to 3 constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 is constant pressure heat rejection. So this is pressure constant process, this is entropy constant process 1 to 2, this is pressure constant process 2 to 3, and this is entropy constant process 3 to 4. Then we have TS diagram, and TS diagram says that we have 1 to 2 isentropic compression, then 2 to 3 constant pressure heat addition, then 3 to 4 we have isentropic expansion, and 4 to 1 we have heat rejection. So there is basically a Brayton cycle which is generally used in the gas turbine power plant. So these cycles basically constitute different engines. Then they can be internal or external combustion engines, or they can have single or multiple components to constitute the engine, but the idea is to use the heat and reject the heat so that we can have net work which will be done in the thermodynamic process where we have different working mediums. So this is how we complete the review of thermodynamics, where we have learnt basic terminologies of thermodynamics, then we have seen what are the processes which would be important for us, and then we have seen the laws of thermodynamics, and now we have seen that there are cycles upon which engines are based. Now we will take only Brayton cycle here onwards for further discussion, or we might take some other cycle for comparison in the case of our course. Thank you.